Students, today we are learning mathematical induction. Mathematical induction. So, in mathematical induction, there is a principle which is principle of finite mathematical induction. This hereafter it is called as principle of mathematical induction simply. So, principle of mathematical induction, here I am writing. See here, if Pn is any mathematical statement corresponding to natural number n, means for each natural number you can get a statement. That means between natural numbers and statements there will be one correspondence. For each natural number you can get a statement. That kind of mathematical statements are denoted by Pn. So if Pn is a mathematical statement, corresponding to n belongs to n, n being set of natural numbers. Now, if P1 is true, what do you mean by P1 is true? Already I said for each natural number, a mathematical statement will be associated. What is a mathematical statement? What is a statement? Statement means it can be true or false, but not both. So a statement can be true or false. But here in this situation, the P1 must be true. So suppose P1 itself wrong, then nothing to prove. The given statement is wrong. So here P1 must be true. That we have to prove that P1 is true. Next, you have to consider Pm is true for some m belongs to n. So consider Pm is true for some m belongs to n. For some m belongs to n, consider Pm is true. If it implies that Pm plus 1 is also true, as m is a natural number, every natural number will have its successor. We know, we have learned this axiom in early standards. For every natural number, there will be a successor. So as m is a natural number, its successor m plus 1 is also a natural number, obviously. So if Pm plus 1 is also true, then Pm is true for every n belongs to n. For all, the symbol stands for all, universal quantifier. There are two quantifiers in mathematics, universal quantifier and existential quantifier. This is for all, which is universal quantifier, and this is existential quantifier. This is for some. Okay. So this is principle of mathematical induction. This principle is proved. Okay. So because it's a proved statement, it is taken as granted, and if all the conditions in this theorem or success in any mathematical statement. If all these conditions are success, then you can consider that that statement is true for every n belongs to n. So here we are going to do some problems basing on mathematical induction principle. The heading would be prove the following statements using principle of finite mathematical induction or using principle of mathematical induction. Now, first one is, heading is already clear. Prove the following statements using principle of finite mathematical induction. So under that heading, the first question is 1 plus 2 plus 3 plus 4 plus so on plus n is equal to n into n plus 1 by 2. We have to prove this for all n belongs to n. So now proof begins. As a first step, we will consider this statement as Pn. That you have to put it on paper. Pn. Some students will write is equal to, but it is wrong. You should not put is equal to symbol here. Here you should not put is equal to symbol. Here you have to put like 2 dots. So Pn is 1 plus 2 plus 3 plus 4 plus so on plus n is equal to n into n plus 1 by 2. This is Pn. Now, in the principle of mathematical induction, the first step is we have to prove that P1 is true. Now, we will prove how. You see. Now, let us write first what is P1. P1 means the statement associated to natural number 1. So what is the statement associated to natural number 1? 1 is equal to 1 into 1 plus 1 by 2. This has been taken from this original statement. So this is actually P1. Now, we have to see the truthness of this statement. So for that, let us take LHS. LHS is equal to 1. Now let us take RHS. 1 into 1 plus 1 by 2, which is equal to 1 into 2 by 2, which is equal to 1 into 1, which is equal to 1. What you got in LHS, the same you got in RHS. So that you can conclude that LHS is equal to RHS. So as LHS is equal to RHS, you can conclude that P1 is true. So this is some A. So you have arrived to step A. Now, as per mathematical induction principle, now we will consider that for some natural number m, this statement is true. That some natural number is m. So consider that for m belongs to n, Pn is true. So already we are considering it is true. So need not to prove the truthness. Already it is true. We are considering it is true. So it is taken as granted. That's what the mathematical induction is suggesting us. So we are proceeding. as per the mathematical induction principle only. So, what is the statement which you have considered as true? That I am writing it. So, which is 1 plus 2 plus 3 plus 4 plus so on plus m is equal to m into m plus 1 by 2. This you have considered as true. Say for a moment it is 1. So this is the important step. And much more important step is proving that P of n plus 1 is true, which is a crucial step in this solution. So here you have to prove that P of n plus 1 is true. Now to prove that P of n plus 1 is true, so what is that P of n plus 1 which ought to be proved? Which is to be proved. So now let us write first what is that statement which we have to prove. For sake of convenience, I am writing P of n plus 1. Actually, this has to be established. So this is not taken as granted. It has to be established. If you establish this, our problem is finished. So we are seeing our destination little earlier here. So what is to be proved? Here I am writing, which is 1 plus 2 plus 3 plus 4 plus so on plus m plus 1, because we are writing P of m plus 1, which is equal to m plus 1. This m has to be replaced with m plus 1 into m plus 1, which is m plus 2 by 2. This we are supposed to prove. So this is our destination. So how we will reach to this destination? Let us see. This is already a statement which is taken as granted. So you can use this and you can get this. So for that, I am adding m plus 1 on both sides of this equation 1. So you have to mention that adding m plus 1 on both sides of equation 1. Then you get 1 plus 2 plus 3 plus so on plus m, and now we are adding m plus 1. As m plus 1 is added on LHS, the same m plus 1 has to be added on RHS. Now we have to continue this RHS until you see this. Once you saw this, our problem is finished. So now take LCM. Then you get m into m plus 1 plus 2 into m plus 1, which is equal to, take m plus 1 common, m plus 1 into m plus 2 by 2. So you have reached this. So what you are supposed to prove, you have proved that. Isn't it? So therefore, P of m plus 1 is true. So this is, say this is B here, B, so here you write B, this is C. So combining the facts, in A, B and C, you can see the principle of mathematical induction is completely verified. So using principle of mathematical induction, this I am writing MI, mathematical induction. Using principle of mathematical induction, P of n is true for all n belongs to n. So this conclusion is most important. This conclusion has to be given. You can get good marks. So this ends the problem. This is the mathematical induction problem solving procedure. I think you have understood. The next second problem is 1 by 1 into 3 plus 1 by 3 into 5 plus so on. This is equal to n by 2n plus 1. Same procedure. So solution. So in the solution, we start our solution by considering this mathematical statement as Pn, as we did in the previous problem. Same procedure wise, also same. Now we have to first prove that P1 is true. Okay. So now let us write P1. P1 is 1 by 1 into 3 is equal to 1 by that side, right side, in the place of n, you have to put 1. So 1 by 2 into 1 plus 1. This is P1. Now let us see the truthness of this statement. For that, let us take LHS. LHS is equal 1 by 1 into 3. This is into 1 into 3. Some students will mistake it as 1.3. Please don't mistake it as 1.3. It is 1 into 3. Which is equal 1 by 1 into 3 is 3. So now let us take RHS. It's equal 1 by RHS. 2 into 1 plus 1. Which is equal 1 by 2 ones are 2 plus 1, which is 1 by 3. So obviously we have seen LHS and RHS both are same. Therefore LHS is equal RHS. The moment LHS is equal RHS, we can conclude that P1 is true, obviously. So therefore P1 is true. So this step you consider as A. Now for some m belongs to n, consider that Pm is true. This is, we have to consider it is true, need not to prove this. So for some m belongs to n, let Pm is true. Therefore Pm is 1 by 1 into 3 plus 1 by 3 into 5 plus so on, plus 1 by 2m minus 1 into 2m plus 1 is equal m by 2m plus 1. This we have considered as true. So you take this as step B, to which you have reached successfully. So next we have to prove that P of m plus 1 is true. So now let us write that. So now to prove that P of n plus 1 is true, this you have to prove. So what you are required to prove, what you are supposed to prove, that you are taking little in advance. That is to prove that P of m plus 1 is 1 by 1 into 3 plus so on, 1 by 2m minus 1 into 2m plus 1. As you are writing p of m plus 1, you have to take that m plus 1th term also, which is 1 by 2 into m plus 1 minus 1, which is 2m plus 2 minus 1, which is 2m plus 1. 2 into m plus 1 plus 1, which is 2m plus 3. And on right side, that n has to be replaced with the m plus 1. So you get m plus 1 by 2 into m plus 1 plus 1. This you are supposed to prove. This is your destination to which you have to reach. So for this, to get this, we consider this statement because this has already been considered as true. So you can take it as granted. So using this, we have to get this. For that, we have to add that m plus 1th term for this statement on both sides. So you please write, adding 1 by 2m plus 1 into 2m plus 3 on both sides of b. Then what do you get? Tell me. So 1 by 1 into 3 plus 1 by 3 into pi plus so on plus 1 by 2m minus 1 into 2m plus 1 plus 1 by 2m plus 1 into 2m plus 3, and you have to add even on right side, so it is equal to m by 2m plus 1 plus 1 by 2m plus 1 into 2m plus 3. So now, if you continue with RHS, as a first step we take LCM. So the LCM will be 2m plus 1 into 2m plus 3. If you proceed further, you get m into 2m plus 3 plus 1. Now you multiply this, so you get 2m square plus 3m plus 1. Keep the denominator unchanged, 2m plus 1 into 2m plus 3. Now by splitting the middle term, you have to factorize this quadratic expression in the numerator. So it's equal to 2m square plus 2m plus m plus 1 by 2m plus 1 into 2m plus 3. Now, if you take 2m common, take 2m common, here you get m plus 1. If you take 1 common, you get m plus 1. Divided by 2m plus 1 into 2m plus 3. Now on the whole, if you take m plus 1 common, then you get m plus 1 into 2m plus 1 by 2m plus 1 into 2m plus 3. Now this 2m plus 1 get cancelled. Then you are left with m plus 1 by 2m plus 3. So that's what we are supposed to prove, m plus 1 by 2m plus 2 plus 1 2m plus is the same thing you get. Therefore, P of m plus 1 is true. So, step C. Now from A, B and C, it is clearly evident from principle of mathematical induction, P of n is true for all n belongs to n. That statement finally you have to write without fail to get some good marks, and you have to conclude the problem.